in a series of lecture which will discuss the tensor algebra so as to make ourselves accustomed or equipped, make ourselves equipped for the discussion of special relativity in terms of four vectors. Uh, in vector analysis, we have seen that there are two quantities. Say for example, force and acceleration. They are related by such a relation where the force acts in the force and acceleration has the same direction. In that case, the quantity m is known as a scalar, mass is a scalar, but this is not the situation always. As for example, if we consider the angular momentum L of a body of a rigid body moving about a point, then we know that this angular momentum is governed by such a relation. Actually, Lx, if we consider the Lx is I xx omega x plus I xy omega y plus I xz omega z. So the x component of angular momentum depends on x, y and z components of angular velocity, and such a relation cannot be expressed in terms of vectors and scalars, and we have to go for the more generalization of vector, which is the tensor. Another classic example is from elasticity. Consider a wire, and if you stretch it along along the length by along the longitudinal direction by applying, say, some weight, then there is the stress developed along the longitudinal direction as well as in this direction, the lateral direction. Stress also arises in the lateral direction, and one speaks of Poisson ratio. If we want to express such quantities, then the introduction of tensor becomes inevitable. There is another example, is that the Ohm's law. We know that Ohm's law is thus: if we apply such a relation to an isotope, or if we apply the polarization then this quantity, we know that for an isotropic medium, this is a tensor. This chi E susceptibility is a tensor, and so that is to say that Px not only depends on Ex. That is to say, if we apply an electric field along X direction, then polarization arises not only in the X direction as well as in Y and Z direction also. In other words, we may say that if we apply a vector cause along a direction, and if the effect does not remain confined only in the direction of the application of the cause, but the effect also extends in the perpendicular direction, then the introduction of tensor becomes inevitable. All these examples that we have cited so far discusses the tensor of rank 2, which originally was treated in terms of a quantity called dyadic. But the definition of tensor that will be we will learn in this lecture not only applicable is not only applicable to tensor of rank 2, but it can be extended to tensor of any rank. As as for example, if we want to discuss general relativity, then curvature tensor becomes a tensor of rank 4. So with this introduction, we will now introduce ourselves with the definition of tensor. But before going to this, I want to remind you about shorthand notation, which was introduced by Einstein and known as Einstein's summation convention, that will be used extensively in this discussion. Otherwise, the mathematical expression will be lengthy. So we have a quantity like this. We have xi square I is equal to 1 to n. That means we are to calculate this x2 square plus x3 xn square. This is the quantity that we are going to evaluate. In Einstein's summation convention, one rewrites it as simply xi. This is an index which is being repeated, and the Einstein summation convention is that if we have an index which is repeated, then the sum over this index is implied. So to repeat the index we rewrite x as this. And if we want to evaluate this quantity, summation xi I is equal to 1 to n in Einstein's notation, then we must write it root over xi. So the index I is repeated. So it is summed over this. As for example, if we write that AI BI, that means it is A1 B1 plus A2 B2 and so on and so forth, because the indices has been repeated. But if we write it that AI BJ CI, then this means that the summation is over I. So we have A1 BJ C1 plus A2 BJ C2 and so on. This is the Einstein summation convention, which will be used extensively in this discussion. Now coming to definition of tensor, formal definition of tensor. And another thing is that we define a n-dimensional space, real space, n-dimensional real space. Real space. This is mathematically denoted as Rn. That is, if we call a vector x in this dimension, a vector x in this dimension is actually comprises of components x1, x2 up to xn, which is written in brief as xi. This represents the set, or we may write it as a like this. These are the all equivalent notations. This is the meaning of n-dimensional space. Then, to define this n-dimensional space, we introduce a coordinate system S. coordinate system is with axis x1, x2 up to xn. The reason will become clear in next few lectures. Instead of using subscript that we used to do in vector analysis, in tensor analysis we write these as superscript. Remember that these are not powers, these are the superscript. So these are the axes of S frame. And we have another coordinate system, bar system, with coordinate axis x bar 1, x bar 2, up to x bar n. This is simply written as xi, and this is written as x bar alpha. Note that for S system we have used Roman index, and for bar system we have used Greek symbols. We have a quantity of function phi, which phi is defined in S prime, which is a function of all these variables. And we have another one, the function, the same function when expressed in bar system is like this. As for example, consider the phi is equal to x square plus y square plus z square. This is the point lies on the surface of a sphere centered at the origin. So in this case it is x1 square, x2 square, x3 square, which using summation convention, Einstein summation convention, is written as xi. This function phi, when expressed in this coordinate system, if we use a bar system to spherical polar coordinate system, then phi bar is simply r square, that is equal to x bar 1 square in r theta phi coordinate system, and this is equal to rho square plus z square, that is equal to x bar 1 square, x bar 3 square in rho phi z coordinate system. So we say that it is a function phi which in S frame looks like this, and which in prime barred frame looks like this. Here we have cited an example. We define a scalar to be one which is same in both the coordinate system. That is, for a scalar, in Rn, scalar is defined as a quantity which remains invariant, under coordinate transformation. That is, phi, if phi be a scalar, if I have used the word if, then this is must be equal to. One point I want to mention that if we write a vector in one coordinate system, we generally say that the vector A is equal to I cap AX, J cap AY plus K cap AZ. I am still writing this relation in terms of notation we use to define in vector calculus, vector analysis. And we generally say that AX, AY, AZ, they are the scalars, and they are the scalars, and we multiply a vector by a scalar to get another vector. But as for this definition that we have put forward over here, AX, AY, AZ are not scalar, because if we write the vector A in another coordinate system, then that is in a prime system, then it will be A prime, AX prime, J prime cap, AY prime plus K prime cap, AZ prime. So AX changes to AX prime, which are not same. So the components of a vector, strictly speaking, are not scalars. It is better to say that they are components of a vector. That is to say that the earlier definition of a vector and scalar has to be reformulated. In earlier classes, we have defined a scalar to be a quantity which has only magnitude, no direction. But here, in tensor calculus, we define a scalar to be one which remains invariant under coordinate transformations. Those quantities which do not follow the definition of tensor, they do not come within this purview. As for example, these components of a vector, they cannot be connected in general as a tensor of a suitable rank. Now we come to the definition of a vector. So before going to that, it would be better to cite few more examples of a scalar. Say we have a vector A. The vector is this vector. This is the vector A, which has this much of length. Whichever coordinate system we use, the length, which is the length of the line segment starting from here to there, is same in any coordinate system. That is to say that summation over AI square, in Einstein's notation, it is AI, it is a scalar. It is a scalar. It is a scalar. There is another example, that is, you might know that in Minkowski space of special relativity, x square plus y square plus z square minus c square t square, it is a constant. So we write it as summation over xi square, I ranging from 1 to 4, and we write it like this, and in Einstein's notation is this square x4 is ICT. So it is a scalar, it is also a scalar. So this is a 3 scalar. This is those who have already undergone the course on special relativity, you know that it is a scalar in Galilean form. So it is a 3 scalar, and this is also a scalar in Minkowski's 4D Minkowski space. So it is a Lorentz scalar. So it is a four scalar. So we may call it as Galilean scalar. It is a Galilean scalar and it is a Lorentz scalar. In tensor, now we come to the definition of vector. In tensor analysis, there are two kinds of vector. One is known as the covariant vector, another one is known as the contravariant vector. Let us first define or put forward the formal definition of vectors, and then we shall, as the time goes, we shall explore and try to reconcile the present definition with the definition we are habituated with. A contravariant vector. In Rn, in n-dimensional real space, a set of n quantities the quantities are ai, which are the functions of xj in S frame, and a bar alpha, which is a function of x bar beta in S prime, are said to be the components of a contravariant vector if they transform as well, the definition, this is the definition, ai, which is a function of all these things. But sum over alpha is there. In other words, this is written in Einstein's notation, it is written as the inverse relation is the inverse relation being relation is a bar alpha ai. If a set of quantities a and a bar transform following this relation, then they are said to be the components of a contravariant vector or contravariant vector. If we are in dealing with the three-dimensional space, then there are three such components. If we are dealing with a four-dimensional space, then ai has four values, a bar also has four values. And in general, if we are dealing in an n-dimensional space, then this has n values as well. These also have n values. Uh, if we have these two are not independent relation, we can start from this and land up over here or the converse. We shall show it. Before doing that, we want to write, say that xi. If we write xi, it is a function of x bar alpha. As for example, consider x as the Cartesian system. So x is equal to r sine theta cos phi. So this is x1 is a function of x bar 1 sine of x bar 2 cos of x bar 3. So x1 is a function of x, in general the set of x bars. So this is so a change in xi. This is as per the law of partial derivatives. This is the sum over alpha is equal to 1 to n del xi del x bar alpha d bar alpha. So in Einstein's notation, this is del xi del x bar alpha dx bar alpha. So to say the components of an infinitesimal displacement dr, they are the vector, contravariant vector. You match this definition with this. So we see the components of this dr the components, they are the components of a contravariant vector. That is the reason due to which we have written you have used superscript instead of subscript that we are habituated of doing in vector analysis. There are firstly, I want to show that we can come from this relation to this or the converse. In doing this, we define such a quantity dxi, dxj. This can be written as del xi, del x bar alpha, del x bar alpha, del xj. And the quantity on the left hand side is 1 when I is equal to j, and it is 0 when I not equal to j, because xi's are independent of each other. That is to say, it should be a Kronecker delta, and this is we write ij. Usually we used to write Kronecker delta as ij. Now this definition has changed to ij, and the same thing, this is equal to 1 for I is equal to j and 0 for I not equal to j. And in the board system, we write it as alpha beta these are the definitions of Kronecker delta. So we start with this expression and will come to this relation. So the relation that will be important is the definition of delta function, delta ij. Xj and delta bar alpha beta these relations will be used very often. So what we do, we start with this relation and multiply this relation so on the right hand side we have del xi del x bar alpha del x bar beta del xi a bar alpha and sum over r. So here we do not to write sum explicitly because there is a repetition of index. Here also the repetition of index, so we need not to write this explicitly. But what is when we carry out this sum, this becomes a bar alpha, and from this part we get delta of beta alpha, because this part is the Kronecker delta in Bott system beta alpha. Just and when we carry out the sum over alpha, the repeated index, this is called the dummy index, and beta is called the free index, we get a bar beta. So the a bar beta is equal to del x bar beta del xi ar. If we replace the free index beta by alpha, we get this relation. So this inverse relation is not an independent relation. It can be derived from this also. We come to some examples of covariant vectors. Now, covariant vector, examples of covariant vectors, the velocity and acceleration are the examples of covariant vectors. Examples of covariant vectors. These are the velocity and acceleration. They are. Now, if we define velocity in S prime, so this is actually dxi dt. This is the component of velocity in S prime, and this definition in Bott form is we differentiate the quantity with respect to a scalar. You remember that here the differentiation is carried out in terms of a scalar. Otherwise, there may be some problem that we shall discuss later on. When we shall use this time derivative in special relativity, then we must differentiate with respect to a Lorentz scalar. That is, in that case, it should be proper time tau, not the Galilean time. Now we know the relation that del xi is equal to del xi so pi is equal to del xi Lx bar alpha, v bar alpha. Match this definition like this one. So velocities, the components of velocities are the components of contravariant vector. Now coming to acceleration. Now coming to the definition acceleration. The components of acceleration are defined as the time derivatives of velocity. So AI is equal to the and A bar alpha is equal to. So what is this? We start with this definition. And in earlier occasion we have obtained the transformation relation of the components of velocity. Recall that we have shown that the velocity components are transformed like the components of a contravariant vector. So we have used this relation. So this time derivative once operates on this, another once on this. So we have del 2xr in general, the coordinate transformation that we talk about do not depend on the parameter time t, so this is 0, and we are left with del x bar alpha, and this is a bar alpha. So we see that the velocity and acceleration, they transform as the component of contravariant vector. This much for today. In the next class we shall introduce the covariant vector.